Hello, in today's video we're going to be talking about section 8.1 on sequences and their notation. So to give a brief introduction of sequences, we'll say a video game company launches an exciting new advertising campaign. They predict the number of online visits to their website will double each day. The model they are using shows 2 hits the first day, then 4, then 8, and so on. If their model continues, how many will there be at the end of the month? So this sequence is what we call geometric. It has a pattern and it is multiplying by 2. So we start with the number 2, then 4, then 8, then 6, then 32. So a sequence, what we're going to be talking about specifically in section 8.2 and 8.3, can be either geometric, such as this one, where we are multiplying to get from one number in the list to the next. It can be arithmetic, meaning we're adding to get from one number in the list to the next, or it could be neither, meaning we have another pattern or no pattern at all. So a sequence is essentially a list of numbers. Arithmetic sequences, as I very briefly mentioned just a moment ago, have a common difference. So for example, maybe I start with the number 5, the next number in the list could be 8, giving me a common difference of 3, meaning that the pattern here to get from one number to the next in the list is that we are adding 3. So if I add 3, the next number would be 11, then 14, then 17, then 20, and so on. Sequences can be what we call infinite, meaning such as this one, there is no ending value. The sequence goes on infinitely, we just continue adding 3. Or they can be finite, meaning that at some point there is an end. So maybe in this case I end at the number 35. So I start at 5, end at 35, and that is all for my sequence. Now a few pieces of terminology that I want to talk about. These apply to, at least these first 3, apply to all sequences, not just arithmetic sequences. A sub 1, A represents the term value, 1 represents the place that it's in your list. So what this notation is saying is I want to know what the first term in the list is. A2 is saying I want to know the second term or the second value in my list. A sub n is saying the nth term. So in this case, my first term, A sub 1, is going to be 5. The very first term, or the term occupying place 1, is 5. The second term, or the term occupying place 2 in my list, is 8. And the nth term says we can plug in any value of n and obtain that value. So here, with what we're working with at this point, I can't identify the nth term because we don't know what place we're looking at. But I'm going to take us through the explicit formula in a moment, which will help us find that nth term. D in arithmetic sequences only is our common difference, meaning it's the number that we are adding or subtracting repeatedly to get from one term to the next in our arithmetic sequence. So in here, we are adding 3, so our common difference is a positive 3. Now, explicit formula for arithmetic sequences says, I have a formula, and if I replace n, then I will determine what place that term has. So for example, if I want to know the third term in my line, then I should be able to replace my n with 3 and determine what the value of that term is. The first term in my list is 5, so I'm going to go ahead and start with 5. Then to get to the next term in the list, we're going to add 3. So to get from 5 to 8, I add 3. To get from 5 to 11, I need to add 3 twice. To get from 5 to 14, I need to add 3 times. So if we're looking at this list, to get to a 5, which is 1, my first term in my list, my n value here is 1. To get to 5, I don't add 3 at all. To get to 8, which has an n value of 2, I add 3 once. To get to 11, which has an n value of 3, I add 3 twice. To get to 14, which has an n value of 4, I add 3 times. So I'm adding that 3 one less time than the place that I'm trying to find. So for example, if I want to know what the first term in line is, well, we know that that's going to be a 5 just based on our sequence, but I'm going to go ahead and use my formula to help me make sure that I did not make any mistakes. So if n is 1, then I should be able to put in a 1 to my equation, and my result we're hoping should be a 5 because we know that's the first term in our sequence. And sure enough, 5 plus 0 is 0, so A1 is equal to 5, just as we expected. If I back up, let me try this explicit formula for maybe the 1, 2, 3, 4, 5th term in line, which we know should be 17. If I plug in a 5, I want the 5th term in line. I start at 5, and then I add on the number 3, 5 minus 1 times, because I want the 5th term in line. So I'm only adding 3 4 times. So I start with 5 and I add 3 1, 2, 3, 4 times. Sure enough, A5 is 5 plus 12, and just as we expected, A5 is 17. So our explicit formula for any arithmetic sequence can be found by starting with your first term, A1, and then adding on your common difference, n minus 1 times. This will be our explicit formula for any arithmetic sequence. Now there are other sequences, such as geometric, or maybe a sequence that doesn't follow either of those patterns, that won't use this for their explicit formula, but specifically for arithmetic, that is the formula that we can use. So we're going to write terms defined by the sequence. So determining the nth term, a sub n, for this equation, I'm going to go ahead and start by creating a list, just getting an idea of what's happening in my sequence. So A1, I see that A1 here is 2, A2 is 4, A sub n, I need to go through and find by using my explicit formula, which is A sub n equals A1 plus my common difference times n minus 1. So I need to know my common difference. Well, looking at this sequence, I've got 2 plus 2 is 4, 4 plus 2 is 6, not 8. So we have a problem. This sequence is actually geometric in nature because we are multiplying to get from one term to the next. So we actually cannot use the explicit formula that we have for arithmetic sequences. Since there is no common difference, this is not an arithmetic sequence. So I need another way to write my explicit formula. I can still find a sub n, I just need to identify my pattern. So my pattern here is that I start at the number 2, and then I'm going to be multiplying that starting number by 2 repeatedly. So to get to the second term in line, I multiply by 2 once. To get to the third term in line, I multiply by 2 twice. Well, repeated multiplication is shown with exponents, so I'm going to multiply by 2 one less time than the number I'm trying to find. So for geometric, we can take our a sub n and find that n, that nth term, by multiplying our first term in line by what we call the common ratio to the power of n minus 1. These formulas aren't super important right now. What's more important is just processing through the concept of creating the explicit formula. So you don't need to worry at this case about memorizing these explicit formulas, but we do need to be comfortable getting here. And then in sections 8.2 and 8.3, we're going to be talking more about those explicit formulas for arithmetic and geometric sequences. So go ahead, take a moment, pause the video, and write the explicit formula for each sequence, meaning a sub n equals, and then something in terms of n on that right-hand side. So pause the video and do that now. These are all arithmetic sequences, so we can, if you do choose to use the formula, you can use that. I would just have 17 plus 2 times n minus 1. You may have even chosen to simplify. You would have 15 plus 2 times n as your explicit formula. Either of these would be okay. In number 2, I start at the number 25, and then I see that I'm adding on 200 n minus 1 times. In number 3, I start at the number 20, and then I see that I'm adding on 7 to every n except the first one. And then in number 4, I see that I'm starting at negative 27, and I'm subtracting 20 to get to any n except the first one. In example 812, I'd like you to take a moment to pause the video and see if you can identify the first 5 terms of each sequence represented by the explicit formulas here. So in other words, you are finding A1, A2, A3, A4, and A5 for each of these 2 sequences. Go ahead and pause the video and do that now. So all we are doing for A is we are replacing the n value with the n that we are asked to find. So for A1, I'm replacing all the n's with A1, and then I simplify and find that I get negative 1/2, and then we repeat that process for the following 5 terms. For B, our first 5 terms are going to be the fractions that I've written here, which do reduce down to negative 2. Here I've got a positive 2. Here I've got a negative 3/2. Here I've got a positive 1, and dividing by 4, I have a negative 5/8. In example 813, we'd like to write the explicit formula for each sequence given below. So these ones are probably going to take a little bit of puzzling through to identify exactly what's happening in each of these sequences. But your goal, again, is to write a formula in terms of n for each of these sequences. So pause the video and try that out on your own now. So the first thing that I see is I see this alternating sign, which tells me that I'm going to have a negative 1 to the power of n. Negative 1 to the first power is negative 1, second power will give me positive 1, third power negative 1, and so on. So that's where I'm going to start. Then I see that in my numerator, I go 2, 3, 4, and it looks like I'm just adding 1. So I'm going to go ahead and start with n, which in my first case would be a 1. So I need to add 1 to that n. That would give me 2, then 3, then 4, then so on. Now in my denominators, I see that I'm starting with 11 and then going to 13 and 15, and we are adding 2 for each denominator in my list. So what I can do is say that my n in this denominator needs to be 1 for that first term. First term always has an n value of 1. But I need to get from 1 to 11. So there's a few different ways I can do that. I can add 10 to my n, and then 10 plus 1 would give me 11. Here n is 2, but 10 plus 2 does not give me 13, so that's a bit of a problem. So another option here to get from 1 to 11 is I can double my n and add 9. That gives me 11. 2 times 1 is 2, plus 9 is 11. There's my 11. Now for my second term, n is 2, I should get 13. 2 times 2 is 4, plus 9 is 13, and sure enough, there we go. So the reason I knew to multiply by 2 is because we are making a jump of 2 for each increase in my denominator. So my explicit formula for A is going to look something like this. In B, A sub n is going to have a numerator of negative 2. That negative 2 doesn't seem to change throughout the entire list that I'm working on, but the denominator does seem to change. It looks like I go from 25 to 125 to 625 and so on, and this looks geometric. It looks like we are starting at 25, and then we're multiplying by 5 for every hop that we make thereafter, so 5 to the power of n minus 1. So my denominator, I start at 25, and then I multiply by 5 for every term except the first one. And similarly in C, it looks like I start with the number 9, and then I'm going to be multiplying by what looks like a negative 9 to get to every term after the first one, so to the power of n minus 1. And that brings us to the end of our introduction on sequences and explicit formulas. Thanks so much for watching and have a great rest of your day.